Hello friends, my name is Mradul Kumar Jain, Assistant Professor in Ajay Kumar Garg Engineering College. Today we will discuss Poset, totally ordered set and chains. So starting from the Poset, first I will discuss about the equivalence relation. A relation is called equivalence relation if it is following a set of property. That means a relation must be the reflexive relation, symmetric relation and transitive relation. Suppose we have a set of elements, suppose we have a set S and having three elements 1, 2 and 3, and when a relation will be called as the reflexive relation. Suppose there is a set S having three elements 1, 2, 3, and if there exists the pair like A comma A for all A belongs to S. If for each and every element of S there exists A comma E type of element, then we can say the relation is reflexive. So for this, for if the set is S and the elements are 1, 2, 3, then we should have 1 comma 1, 2 comma 2 and 3 comma 3. These pairs should necessarily exist, and if there exists other pair, it doesn't matter. Then the relation will be the reflexive. When the relation will be symmetric, if suppose there exists a element A comma B, then there must be image pair B comma A. For each and every pair, there should be the image pair. Then the relation will be symmetric. For each and every pair, there should be B comma A. And a relation should be transitive. When a relation will be transitive, suppose there exists a pair, a set of pair A comma B and B comma C. First element is related to the second element and the second element is related to the third element. Then there should be a relation from first element of first pair and second element of second pair, A comma C. If these three property holds at the same time, then we can say the relation will be the equivalence relation. Similar type of relation, there exists another relation which is known as the partial order relation. When a relation will be known as the partial order relation, if a relation is reflexive, antisymmetric and transitive. When the relation will be the equivalence relation, when it is reflexive, symmetric and transitive, and when the relation will be the Poset, if it is reflexive, antisymmetric and transitive. If these three property holds at the same time, then we can say the relation is the partial order set or the Poset. So we already know when the relation will be the reflexive, if there exists A comma A type of element for all A belongs to S. When the relation will be the antisymmetric, the condition of antisymmetric is if there exists A comma B, then there must exist B comma A. But the condition is A must be equal to B. A must be equal to B. So if we have a relation and this contains A comma B of type of element and there exists the image pair B comma A, and the condition, what is the condition? A equal to B. So when this condition will be hold, that means if A equal to B, that means it should be either A comma A or B comma B type of element. Only then this condition will be hold. So when this condition will be hold, suppose we have a set of element 1, 2, 3. So 1, 2, 3. So how many of ordered pair will exist in this for this set? So this contains 1 comma 1, 1 comma 2, 1 comma 3, 2 comma 1, 2 comma 2, 2 comma 3, 3 comma 1, 3 comma 2 and 3 comma 3. So in this matrix or matrix of ordered pair, you can see there exists a diagonal element which contains 1 comma 1, 2 comma 2 and 3 comma 3. Only for these elements we can say that there exists a ordered pair for which there exists a comma B and B comma A. For this A equal to B. Only if the ordered pair of these diagonal elements exist in a relation, then we can say this particular relation will be the antisymmetric. There should not be any image pair for which suppose there exists a 1, 2 and 2, 1. In such a case, we cannot say that the relation will be the antisymmetric, because antisymmetric says there should be the image pair. That means if there exists 1, 2, then there cannot be 2, 1, because we are saying the condition is that A equal to B. So this condition will be possible only for the diagonal elements. I will take some examples also. And transitive relation is, I have already told you in equivalence relation, if there exists two pair A comma B and B comma C, we have these two pairs. If we have these two pairs, then there must be A comma C. If these three property holds at the same time, then we can say the relation is the Poset. So let's see some examples. Suppose there is a set S having three elements 1, 2, 3, and we will consider the different type of relation. So first is the R1. This contains 1, 1, 2, 2, 3, 3, 1, 2, 3, 1, 3, 2, and we have to check that this particular relation is the Poset or not. So I have already told you a relation will be Poset if it is holding the three property, reflexivity, symmetry and the transitivity. So we can see that there exists 1, 1, 2, 2, 3, 3. So that means this type of pairs is necessary for the reflexive relation. So this relation is clearly, we can see that this relation is the reflexive. For the antisymmetric, we have to check that there should not be A comma B for which there exists B comma A, where A is not equal to B. So we can check if there exists 1, 2, there must not be 2, 1. If there exists 3, 1, there must not be 1, 3. If there exists 3, 2, there must not be 2, 3. Because same type of, for this type of elements, the image pair should not exist for the antisymmetric relation. Only for this type of elements, the image pair exists. So this particular, and we have to check the transitivity. For transitivity, we already know that if there exists A is related to B and B is related to C, then there must be A is related to C. So we will check for each and every set of pairs. So if this is 1, 1, then we will check this element, because 1 is related to 1 and 1 is related to 2, then there must be 1 is related to C. So that means there must be 1, 2 and 1, 2 exist. Again we will check there exists any pair which starts from 1. No such type of pair exists. Now we will consider 2, 2. 2, 2, there exists any pair which starts from 2. There exists no such type of pair. Now we will consider 3, 3. There are two pairs which starts from 3. First one is 3, 1 and second one is 3, 2, and we will check for both these two pairs. 3, 3, if 3 is related to 3 and 3 is related to 1, then there must be 3 is related to 1. 3 is 1 is already exist. Now we will check for this element 3, 3 with 3, 2. 3 is related to 3 and 3 is related to 2. So there must be 3, 2. Again there exists a 3, 2. Now I will check for 1, 2. Any element which starts from 2. 1 is related to 2 and 2 is related to 2. So there must be 1 is related to 2 already exist. Okay. And now we will consider 3, 1. 3 is related to 1 and 1 is related to 1. There must be 3, 1 and 3, 1 is exist. Now I will consider 3, 2. 3 is related to 2 and 2 is related to 2. There must be 3 is related to 2. So 3 is related to 2 also exists, because the reflexivity and symmetry and transitivity, all three conditions holds for this particular relation. So we can say this is the Poset. it will be the poset. Okay, now we will consider another relation for the same set S is equal to 1, 2, 3. So you can see there exists 1, 1, 2, 2 and 3, 3. So this relation is reflexive. Now we have to check it is symmetric or not. So there exists 1, 2 and 2, 1. A is related to B and B is related to A, but A is not equal to B. There exists A, B and B, A, but A is not equal to B. So this relation is not the antisymmetric relation. So if this relation is not antisymmetric, then there is no need to check the transitivity. It will not be the poset. Now I will consider the third one. This relation is reflexive because it contains 1, 1, 2, 2 and 3, 3. It is also the antisymmetric relation because if there exists A, B and B, A, then there must be A equal to B, or I have already told you that only the diagonal type of elements which contains A, or B, B or C, C, then the relation always be the antisymmetric relation. So this contains only the diagonal elements. So we can say this will be the antisymmetric relation. Similarly, it is holding the transitivity property because if there exists A, B and B, C, then there must be A, C. If such type of pair exists, then there must be the A, C for each such type of pairs A, B and B, C. So we can easily check this relation is the transitive because it is holding all the three relation property, reflexive, antisymmetric and transitive. So this relation will be the poset. So again this will be the poset. Now I will check the fourth one. 1, 1, 2, 2, 3, 3. With the help of these three pairs, we can say this relation will be the reflexive. And for 1, 2, there does not exist, because there does not exist 2, 1. Okay, so this relation is the anti-symmetric relation because only for the diagonal elements there exist 1, 1, 2, 2 and 3, 3. So this again it will be the poset. Now the next one, R5. This is the relation having no ordered pair, or we can say the empty relation. So a relation is empty, then it will be the reflexive. No, it will not be the reflexive because for the reflexive relation it is very much necessary there should be A, for each and every element of the set. If this particular set of elements is not available, then we cannot see or we cannot say that this relation will be the reflexive because it is not the reflexive. Because this relation is not reflexive, so it will not be the poset because for the poset it is very much necessary a relation must be reflexive, antisymmetric and transitive. If the relation is not reflexive, then there is no need to check the symmetry, antisymmetry and the transitivity. So this relation will not be the poset. ये poset नहीं होगा. It will be not the poset. Now check the S cross S. We know that the S contains three elements 1, 2, 3. So S cross S contains all type of elements having the diagonal elements, having the image pair of each and every element. Okay, so if S cross S, that means the diagonal elements will be the like of A, 1, 1, 2, 2 and 3, 3. But in the upper triangular and lower triangular matrix, you will see the image pair of each and every element. That means that if there exists a image pair 1, 2, then in the lower matrix, triangular matrix, you will see the 2, 1. If such type of pair exists, then the relation cannot be antisymmetric. Okay, if the relation is not the antisymmetric, then it cannot be the poset. So this relation will not be the poset. Next example is Suppose there exists a relation, or there is a relation R1 which contains A comma B type of element. Okay, and it is defined over the set of integers. We have the integers, and we know that the integer contains negative integers, 0 and positive integers, and the relation is A is less than B. We have the numbers Z, all the integers, negative, 0 and positive integers. We have a relation A is less than B. So first we will find out what is the relation. Relation says it contains the ordered pair which holds the condition A is less than B. So first we will write the ordered pair. So 1 is less than 2, 1 is less than 3, 1 is less than 4, 1 is less than 5, and so on. Similarly for 2, 2 is less than 3, 2 is less than 4, 2 is less than 5, 2 is less than 6. This type of element it will hold. Now we have to check the condition of reflexivity, symmetric and transitivity. Because for the partial order set or the Poset, these three conditions must hold. So for the reflexivity says it should have A comma A. Okay, but for A comma A, this relation holds. A is less than A because our relation is A is less than B. But for such type of ordered pair, the condition will be A is less than A, and it is not possible. So that means if for this condition, if such type of pair does not exist, then the relation cannot be reflexive. If the relation is not reflexive, then we cannot say, or then it will not be the partial order set or the Poset. And there is no need to check the symmetry and the transitivity, because if the relation is not reflexive, then it cannot be the Poset. Because for the Poset, it is very much necessary the relation must be reflexive, antisymmetric and transitive. Now see another example. We have 4 elements, 3, 4, 5 and 6. Condition or the relation condition is less than and equal to. Less than and equal to. And we have to check that this type of set of elements with respect to less than and equal to, it will make a Poset or not. So before checking it will be the Poset, we have to find out the relation. Okay, so first we will create a relation. So I will create ordered pair for this condition having 4 elements and the condition is less than and equal to. So starting from the 3, I will check 3 with other elements. So 3 is less than 4, less than and equal to 4. 3 is less than and equal to 5. 3 is less than and equal to 6. Similarly, I will create a ordered pair for 4 for this condition. 4 is less than 5. 4 is less than 6. Similarly for 5, 5 is less than and equal to 6. There will be only one ordered pair. Similarly, there exists 3, 3 because A3 is less than and equal to 3. Here is the relation is less than and equal to. So we can make this type of pair also. And there exists 4, 4, 5, 5 and 6, 6. And it's the same. That means it contains this type of these ordered pair. If this relation contains these ordered pair, then we can create a graph also. Because there are 4 elements, 3, 4, 5 and 6. And there exists an edge which starts from 3 and will end at 4. So 3, 4, this will the ordered pair can be represented by this edge. 3, 5, 3, 6, 4, 5, 4 comma 5, 4 is this much and 5 is this much, 4 comma 5, 4 comma 6, 4 comma 6, 5 comma 6, 5 comma 6, 3 comma 3, this will be the self loop, 3 comma 3, 4 comma 4, this will be the 5 comma 5 and 6 comma 6. So each and every relation can also be represented by the Poset. So now I have to check this particular relation or the graph will be the Poset or not. So we have to check again reflexivity, symmetry and transitivity. So for the reflexive, there must be A comma A. For all A belongs to set S, and set S is 3, 4, 5, 6. And in this relation you can see there exists A comma A, 3 comma 3, 4 comma 4, 5 comma 5, 6 comma 6. So this relation will be the reflexive. Now we have to check the antisymmetric. Is the relation is antisymmetric? And antisymmetric, what's the definition is antisymmetric? A comma B. If there exists A comma B, there must be B comma A, but A should be equal to B. That means only for the diagonal elements must exist. Only for the image pair exists only for the diagonal elements or for the reflexive pairs. Okay, so for 3 comma 4 there must not be 4 comma 3, 3 comma 5 there must not be 5 comma 3, 3 comma 6 there must not be 6 comma 3, 4 5 there must not be 5 comma 4, 4 comma 6 there must not be 6 comma 4, 5 comma 6 there must not be 6 comma 5. Only 3 comma 3, 4 comma 4, 5 comma 4 and 6 comma 6 exists. So if this type of pair exists, then the relation will be the antisymmetric. Similarly, we will check the transitivity. If the relation is related to 3 comma 4, then I will check the pairs which starts from 4. 3 comma 4, 4 comma 5. There must be 3 comma 5. 3 comma 5 exists. 3 comma 4, 4 comma 6. There must be 3 comma 6. 3 comma 6 exists. 3 comma 4, 4 comma 4. That means 3 comma 4, 3 comma 4 exists. So for 3 comma 4, and the element which starts from 4, it is transitive. Now I will check the 3 comma 5. 3 comma 5, I will find out the pairs which starts from 5. 3 comma 5, 5 comma 6, 3 comma 6, 3 comma 6 exists. 3 comma 5, 5 comma 5, 3 comma 5 must exist. Only there exist 2 pairs. Now I will check the 3 comma 6. 3 comma 6, I will find out the pairs which starts from 6. 3 comma 6 start from 6. There is only one element, 3 comma 6 and 6 comma 6. There must be 3 comma 6, 3 and 6. A is related to C. So 3 comma 6 it also exists. Now I will check for the 4 5. 4 comma 5 I will check all the pairs which start from 5. 4 comma 5, 5 comma 5. There must be 4 comma 5 and 5 comma 5 exist. Now I will check the 4 comma 6. I will check the elements which start from 6. 4 comma 6, 6 comma 6. There must be 4 comma 6 already exist. 5 comma 6. Now I will check the elements which start from 6. 5 comma 6, 6 comma 6. There must be 5 comma 6. 5 comma 6 exist. Now I will check for the 3 comma 3. I will find out the elements or the ordered pair which start from 3. 3 comma 3 and 3 comma 4. There must be 3 comma 4 already exist. 3 comma 3, 3 comma 5. There must be 3 comma 5. 3 comma 5 exist. 3 comma 3, 3 comma 6. There must be 3 comma 6. 3 comma 6 exist. So I have completed. Now I will check for 4 comma 4. 4 comma 4 and it starts from 4 comma 5. There must be 4 comma 5 already exist. It has also been complete. 5 comma 5. I will find out the pairs which starts from 5. 5 comma 5. Then this is 5 comma 6. So there must be 5 comma 6. 5 comma 6 is already exist. Now I will check the 6 comma 6. I will find out the elements which starts from 6. So there is no element which starts from 6. So there is no need to check this particular pair for the transitivity. So for each and every pair where exists A comma B and B comma C, for each and every such type of pairs, there exists A comma C. So we can say this relation will be the transitive relation. So this particular relation will be the Poset. Now another example, the relation is D12. What does it means the D12. D represent the relation of divisibility. And this contains the numbers or the integers which can divide 12 starting from 1 to 12. I will consider the number from 1 to 12, and it contains only those elements that can divide 12. So from starting 1 to 12, I have to check which numbers can divide the 12. So 1 can divide the 12, 2 can divide the 12, 3 can divide 12, 4 can divide 12, 5 cannot divide 12 completely, 6 can divide 12, 7 cannot divide 12, 8 cannot divide 12, 9 cannot divide 12, 10 cannot divide 12, 11 cannot divide 12, and 12 can divide 12 one time. Okay, so it contains the numbers 1, 2, 3, 4, 5, 1, 2, 3, 4, 6 and 12. These are the numbers that can divide 12. And the relation is the divisibility. D represents divisibility. So for this particular purpose, the same time which I was speaking, that 1 can divide 12, 1 can divide 3, 1 can divide 4, 1 can divide 6, 1 can divide 12. I have to create a pair for divisibility. Similarly, 2 can divide 4, 2 can divide 6, 2 can divide 12, 3 can divide 6, 3 can divide 12, 4 can divide 12, 6 can divide 12, 1 can divide 1, 2 can divide 2, 3 can divide 3, 4, 5, 6 and 12. So for this particular divisibility condition, the relation contains such type of pairs. Now we have to check that this particular relation is the reflexive or not. So I have to check A comma A for this elements, because the set is, this time the set is 1, 2, 3, 4, 6 and 12. Okay, so there exists A comma A for all A. So there exists 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, 6 comma 6 and 12 comma 12. So there exist these pairs. So this relation is reflexive. Now I have to check the antisymmetric. If there exists A comma B, there must be B comma A only if and only if A is equal to B. That means I have already told you, it contains only, it is possible only for when A comma A type of element exists, or we can say there exists image pair only for the diagonal elements. So for 1 comma 2 there must not be 2 comma 1, 1 comma 3 there must not be 3 comma 1, 1 comma 4 there must not be 4 comma 1, 1 6 not 6 1, 1 comma 12 there must not be 12 comma 1, 2 comma 4 there must not be 4 comma 2, 2 comma 6 there must not be 6 comma 2, 2 comma 12 there must not be 12 comma 2, 3 6 there must not be 6 3, 3 12 there must not be 12 3, 4 12 there must not be 12 4, there must not be 12 6, and for this these type of pair can exist. So this relation is symmetric. Now we have to check the transitive. Again I have already told you that you can easily check if there exists A comma B type, A comma B and B comma C, then there must be A comma C. If this type of pair exists, then the relation will be the transitive. So this relation is transitive. If the relation is reflexive, antisymmetric and transitive, then we can say this relation will be the Poset. Similarly, you can check that there is a subset of relation, then and the Poset is, and we have to check for the power set. So we will first create a power set, then we will find all, we can write all the ordered pair for this particular subset of relations. Then we can check this particular a relation having this type of pairs, then this particular relation will be the Poset. You can check. And the last topic is comparable and incomparable elements. Two elements can be compared if you can check either A is less than B or B is less than A. The relation is maybe the less than and equal to, or maybe the subset. We have a power set of ABC, and it contains suppose one pair A comma C, and A comma C is not a subset of A comma B. We cannot say. Similarly, A comma B is not a subset of A comma C. If you cannot write in such a way that this particular relation holds between two pairs of element, then we cannot say, or we can say these two elements are not comparable. But if the elements are A comma B and A, B, C, then we can say this particular element is a subset of this element. If you can compare, then you can write in such a way, then these two elements are comparable. Totally ordered set is, suppose there is a set of elements, and if you will consider only two elements for each and every two elements, if you can compare these two elements, then we can say this particular set of elements will create a chain or the totally ordered set. So suppose we have Z integers, and suppose we have to consider two elements 4 or 11. We can write in such a way that 4 is less than or equal to 11. Similarly, for 7 and 9, suppose we are taking the two elements 7 or 9, then we can write in such a way 7 is less than or equal to 9. So we can say, if you add for each and every element, we can compare this element is greater than or equal to second element. So this particular set of elements or the integer will create a totally ordered set or the chain. Similarly, if suppose there exists we have the Z and the relation is divisibility, and we will consider the two element 3 or 9, or we can say 3 can divide 9. That means in such a way we can say 3 and 9 are comparable. But if we will consider two elements 7 and 5, and for the divisibility 7 cannot 7 or 5 or 9 and 5, and 9 cannot divide 5, or 5 cannot divide 9. So we can say these two elements are non-comparable. So thank you. In this lecture we have seen what is the equivalence relation, what is the Poset, what is totally ordered set, and when the elements are comparable and non-comparable. So this is the total glimpse of this particular lecture. Okay, thank you.